question and answer on gravitation. We have to answer these. You can shield a charge from electrical forces by putting it inside a hollow conductor. Can you shield a body from the gravitational influence of a nearby matter by putting it inside a hollow sphere or by some other means? The answer is no. Gravitational influence or force is independent of the medium. Though this can be saved, means a shield can be provided from electrical forces, this cannot be done for gravitational. Means gravitational force, they are independent of the medium. A body cannot be shielded from the gravitational influence of nearby matter. The second is an astronaut inside a small spaceship orbiting around the Earth cannot detect gravity if the space station orbiting around the Earth has larger size, so the size has increased. Can he hope to detect gravity? The answer is yes, because the size of spaceship is now large. You say that the size has increased. The gravitational effect of spaceship may become measurable, and the variation in gravity can also be detected by the astronaut. If you compare the gravitational force on Earth due to Sun to that due to Moon, you would find that Sun's pull is greater than the Moon's pull. But the tidal effect of the Moon's pull is greater than the tidal effect of Sun. Why? First of all, Moon is closer than Earth, so tidal effect depends inversely on the cube of the distance, say r cube. But the force, they are inversely proportional to the square of the distance. Since the distance of Moon from ocean water is very small as compared to the distance of Sun from the ocean water on Earth, so the tidal effect of Moon's pull is greater. This goes small, this goes greater. This is greater than the tidal effect of the Sun. Next is acceleration due to gravity increases or decreases with increasing altitude. If you go up, gravity will decrease. That means decreases. Acceleration due to gravity decreases with increasing depth, and we have to assume that Earth is a uniform density sphere. So if we go down to the center, again it will decrease. In fact, at this point, at the center of the mass, this will become zero. Acceleration due to gravity is independent of the mass of Earth or mass of body. It is not independent of mass of Earth, it is independent of mass of body. The formula minus gm capital M 1 minus r1 minus 1 by r2 is more or less accurate. So it is more accurate than the formula this one, mg r2 minus r1 for the difference of potential energy between two points r2 and r1 distance away from the center of the Earth. The reason being, see, the gravitational potential energy of 2 points r2 and r1 distance away from the center of the Earth can be given by this. Vr1 can be given by minus gmm by r1. Vr2 can be given by gmm by r2. What is the difference in potential energy? Just subtract this from this. We get this expression, and this formula is more accurate than this one. Suppose there existed a planet that went around the Sun twice as fast. So if Earth goes at t, this goes at t by 2. What would be the orbital size as compared to that of the Earth? So the answer is this one. How we arrive at this answer? The time taken by Earth to complete one revolution around the Sun, let us take it as TE, 1 year. The orbital radius, this r, let us take it as RE, radius of the Earth in its orbit. Time taken by the planet to complete one revolution around the Sun, because it is given, if this is t by 2, so it is TE by 2, that is time of Earth by 2, so this is half year. If this is 1 year, it will be 1 by 2 year as given in the question. Let us say that the orbital radius of planet be RP, and we know by Kepler's third law of planetary motion, this t square is directly proportional to the semi-major axis cube. So when we equate for 2, Rp by Re whole cube is equal to Tp by Te whole square. Now take 3 here, it will be in the denominator. So Rp by Re, Tp can be written as Te by 2. Te cancels, half will be there. So half to the power 2 by 3, half is 0.5, 0.5 to the power 2 by 3 is 0.63, which is this one. So the orbital radius of planet will be 0.63 times smaller than that of the Earth. I sub O, one of the satellites of Jupiter, has orbital period of this many days, 1.769 days, and the radius of orbit is this much. Show that the mass of Jupiter is about 1 by 1,000th that of the Sun. So here the orbital period this of Io is given as 1.769. Let us convert it into seconds. So it has 24 days, one day has 24 hours, one day has 24 hours, 24 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. Orbital radius is also given. Let us write here. Satellite, this one, is revolving about the Jupiter. Now the mass of this can be given by mj. Mj represents the mass of this m sub j. Is mass of Jupiter is given by 4 pi r square, 4 pi square, then r, this is again cube, and g and t for, we have taken this t for the orbital of j, tjo, j sub o. So g is the universal gravitational constant. Now let us remember this first equation, we'll be using it. The orbital period of Earth is 365.25 days. So in one day we have 24 hours, 1 hour to 60 minute, 1 minute 60 seconds. So orbital radius of Earth, that is Re, is given by this value. We know this, 1.496 into 10 to the power 11. Now mass of the Sun, ms, is given by 4 pi square, and this is radius of Earth, Re cube, and this is time of Earth, gte whole square. Now when we divide this second equation by the first equation, what do we get? We get this scenario, these two cancel, gg also will get cancelled out. Now these values we have just found out, so just put these values and we get mz by mj equal to 1000. And as you see here, this answer came as 1045, but it is approximately equal to 1000 times. So now it can be inferred that the mass of Jupiter is, if you take it here, 1 by 1000 that of mass of Sun. Let us assume that our galaxy consists of this many stars, each of one solar mass. How long will a star at a distance of this many light years, 50,000 light years from the galactic center, take to complete one revolution? We have to take the diameter of Milky Way to be 10 to the power 5 light year. So what all are given? The R is given this much. So this is in light year. You can convert it into meter by multiplying with this value, 9.46 into 10 to the power 15. This comes around this much. Mass is 2.5 into 10 to the power 11, and solar mass will be what? See, 2.5 into 10 to the power 20. We know that one is this much, one's value is this much, so 2 into 10 to the power 30 we have to multiply, because one solar mass is equal to 2 into 10 to the power 30. So we have to multiply these two so that we get the final value of capital M. Now we know that M is given by 4 pi r square, r cube, gt square. All these values are known to us. We have to find out the time, so take time here and put all these values with the square root. It has to come, then put all the values which are being noted or given here. You get 1.12 into 10 to the power 16 second. Choose the correct alternative. If the zero of potential energy is at infinity, the total energy of orbiting satellite is negative of its kinetic and potential energy. So what will be there? See, if the zero of potential energy is at infinity, the total energy of orbiting satellite will be what? Will be negative of its kinetic energy. So this will be negative of its kinetic energy. The energy required to launch an orbiting satellite out of Earth's gravitational influence is more or less. So it is less than the energy required to project a stationary object at the same height as the satellite out of Earth influence. Does the escape speed of body from the Earth depend on? All these we'll see. See, first of all, we have to know that the escape speed VES is given by under root 2gr, which came from 2 into capital G capital M by R. So these are two expressions. Now the escape speed of a body from the Earth does not depend on the mass. See, the escape speed does not depend on the location also from where the body is projected. Also the escape speed does not depend on the direction of the projection. The escape speed of the body depends on the height of the location from where the body is projected, because the escape velocity depends on the gravitational potential at that point from which it is projected, and this potential will depend on the height as well. So this will be the escape speed depends on the height, because eventually it has come from gravitational potential, which depends eventually on the height. A comet orbits the sun in a highly elliptical orbit. Does the comet have a constant linear speed, angular momentum, angular speed, kinetic energy, potential energy, total energy throughout its orbit? Neglect any mass loss of the comet when it comes very close to the sun. See, the angular momentum and total energy, these are very important. Angular momentum and total energy at all points of the orbit of a comet moving in any highly elliptical orbit around the sun, they will be constant. But the linear speed, angular speed, kinetic and potential energy, they will vary from point to point. So only these two will be yes, that means angular momentum and total energy, others no. Which of the following symptoms is likely to affect an astronaut in space? Swollen feet, swollen face, headache, orientation problem. These three he will be affected, swollen feet may not be. So legs hold the entire mass of a body. You are standing on a ground because there is a gravitational pull. In space, an astronaut feel weightlessness because of the absence of gravity. There is no gravity. So the swollen feet of astronaut do not affect him or her, but swollen face and headaches and space, they or you can say the astronauts will be affected by these. Choose the correct answer for following among the given ones. The gravitational intensity, first we have to see this one. The gravitational intensity at the center of hemispherical shell of uniform mass density has the direction indicated by the arrow. So what is the answer? First, we have to start with a full sphere, means complete sphere. Then we will talk about the hemisphere. So gravitational potential V is constant for at all points in a spherical shell. So the gravitational potential gradient, which is given by dV by dr, is 0 everywhere inside the spherical shell. So the gravitational potential gradient is equal to the negative of gravitational intensity, we know that. So the intensity is also 0 at all points inside the spherical shell. So this is indicating that the gravitational forces acting at a point in spherical shell are symmetric. If now the upper part of the spherical shell is cut out, as you see here, the net gravitational force acting on a body which is located at O will be in the downward direction now. So the gravitational intensity at point, which is defined as the gravitational force per unit mass at that point, will also act in the downward direction. So that the gravitational intensity at point O of this hemispherical shell has a direction as indicated by this arrow, which is downward, C. Now there is another part. We have seen the figure, the direction of gravitational intensity at any arbitrary point, not on the center, but any arbitrary point P is indicated by what? D, E, F or G. So this is the scenario where it goes. Whether it be E again, yes. The gravitational, we will have the same discussion here. The gravitational potential is constant for all points. We'll start with the spherical one. So all points in the spherical shell. So the gravitational potential gradient dV by dr is 0 everywhere inside the spherical shell. And the gravitational potential gradient is equal to the negative of gravitational intensity. So the intensity is also 0 at all points in the spherical shell. So this indicates that the gravitational force acting at a point in a spherical shell are symmetric. Now if the upper part of the shell is cut out, you see in the figure, so the net gravitational force acting on a particle which is at arbitrary point, not at the center, will be in the downward direction. And since this E, since the gravitational intensity at point is defined as the gravitational force per unit area only, at that point it will also act in the downward direction. Thus the gravitational intensity at any arbitrary point P of the hemispherical shell has the direction as indicated by the arrow E here. Okay, this is the direction. A rocket is fired from the earth towards the sun. At what distance from the earth's center is the gravitational force on the rocket 0? Mass of the sun is given, mass of earth is given, we have to neglect effect of other planets, and orbital radius has to be taken as 1.5 into 10 to the power 11 meter. Now this is the scenario. This is sun, this is earth. So mass of sun is this much, mass of earth is this much, the orbital radius is given, r is given. Mass of the rocket, let us assume here to be m. Now let us say that it is x be the distance from the center of the earth where the gravitational force acting on this satellite P becomes 0. With the Newton law of gravitation, we can equate the gravitational force acting on the satellite P under the influence of the sun and the earth, both of them. That is why both are acting, and this is in say a state of gravitational force 0. So what will we do here? We'll take first with the mass of earth. So m is the mass of this object, a body. So g into m into me by x square, this x we have taken, it has to be equal to g into m, again mass of this body, and now mass of sun, this one, and this is the distance r minus x whole square. And now we know all these values, so we can just equate and find out the value of x, which comes to be this value. How will you weigh the sun, that is estimate the sun's mass? The mean orbital radius of earth around the sun is this much. So the orbital radius of earth around the sun, which is given in the question, this is in kilometer, we have changed it into meter. Now time taken by earth to complete one revolution is 1 year, that is 365.25 days. In 1 day there are 24 hours, in 1 hour there are 60 minutes, in 1 minute there are 60 seconds. So we have converted it into second. Gravitational constant, universal gravitational constant, we are aware of 6.67 into 10 to the power minus 11. So the mass of the sun can be calculated using this expression, m equal to 4 pi square r cube by gt square. We have all these values just put in here. This is 2 into 10 to the power 30, and we know this is the mass of the sun, 1 solar mass. A Saturn year is 29.5 times the earth year. So if earth is t, Saturn will be 29.5 t. How far is the Saturn from the sun if the earth is this much kilometer away from the sun? So distance of earth from the sun is given in the question. We'll convert it into meter. This is in kilometer. The time period of earth, if it is te, the time period of Saturn ts will be 29.5 te, which is I explained just now. Now from Kepler third law of planetary motion, we'll take for Saturn and sun. This shows that this rs cube by re cube is equal to ts square by te square. Take rs, take everything on the right hand side, because this ts is equal to 29.5 t, t gets cancelled out. Let it r be like this, 2 to the power 3. Just try to solve it. These are just mathematical calculations, and the distance will come as for this 1.43 into 10 to the power 12 meter. A body weighs 63 Newton on the surface of the earth. What is the gravitational force on it due to the earth at a height which is equal to half the radius of earth? So half is nothing but re by 2, radius of earth by 2. So the weight of the body is 63 Newton, and we know what is the acceleration due to gravity at certain height h. This is given by g dash, which is equal to g by 1 plus h by re whole square, where g is nothing but the acceleration due to gravity. This re is the radius of earth. Now it is given in the question, as I indicated earlier, h is equal to re by 2. Put h equal to re by 2, re gets cancelled, 1 plus 1 by 2, that is 3 by 2, and it is square also. This is equal to 4 by 9 g. Now what will be the mass? Mass w equal to 2 mg, you know this. So this g can be written as 4 by 9 g here, and this is 4 by 9 of the mg. Mg is nothing but weight. 4 by 9 weight is 63 Newton as given in the question. Just 7 9 is 63, 7 4 is 28, it will be 28 Newton. Assuming the earth to be a sphere of uniform mass density, how much would a body weigh halfway down the center of the earth or depth of the earth if it weighted 250 Newton on the surface? The question is like this. If this is the earth radius, then it goes, the depth is this r by 2, d equal to r by 2. So at this point you have to find out if at the surface it was 250 Newton. So weight of the body of mass m at the surface is given by W equal to mg, which is 250 Newton. D is given by half Re, which I explained you here. This Re is nothing but the radius of Earth from this point to this point, means surface to this point, center. So acceleration due to gravity at depth d, gd, is given by g dash equal to 1 minus d by re into g. Just put d equal to re by 2 and it will be half g. So what is the weight of the body at depth d? W dash is mg. Now g dash is half g. Put here half g. This is half into mg, that is mg is w. So this w is given as 250 Newton. Put half into half into 250, that is going to be 125 Newton. Now the rocket is fired vertically with a speed of this much. This is the speed being given from the Earth's surface. How far from the Earth does the rocket go before returning to the Earth? So there has to be some position where its velocity goes 0, it comes back. Mass of Earth is given, mean radius of Earth is given, and gravitational constant is also given. So what will we do here is, velocity is 5 km per second. Let us change it into meter per second, multiplying it by 10 to the power 3. Mass of Earth is given, radius of Earth is given as in the question. Now what is the height being reached? Let us assume it to be h. We will apply the conservation of energy. The total energy of the rocket at the surface of the Earth will be kinetic energy and potential energy, which is half mv square. Potential energy is given by minus g me m by re. Me and re are the values of Earth. Now at highest point h, the final velocity becomes 0. So there will be only potential energy, but it has gone up to some height h. So we have to add re plus h, and half mv square will be 0. So g me m by re plus h. So this becomes 0, and this will simply, because there is no velocity v equal to 0, it is going to return back, so velocity will be 0. Now g me by m by re plus h. So we have this at the surface, and this is the energy at the top where it is going to return back. So total energy, we have to see that it is being conserved. So total energy of rocket at the Earth's surface is equal to the total energy at height h. So this expression we just saw, and this expression has to be equated. We just rearrange it so that we get this half v square equal to 2g, this g re h by re plus h. But we know that this g is given by gm by re square. So we have taken this and put g here. Okay. So we again rearrange, that is, we just rearrange this, so we get this expression, and we take h on the left hand side and others we have to put on the right hand side. Why we have done this? Because all these value we are aware. We just put the value, we get 1.6 into 10 to the power 6 meter. And then this is only h. This is only h. Now we have to add it with the re, radius of Earth, so that we get the height from the center of the Earth. So re plus h, that is 6400 kilometers with this height. Add them with proper units, you get 8 into 10 to the power 6 meter. The escape speed of projectile on Earth's surface is 11.2 km per second. A body is projected out with thrice this speed. So the speed is 3 into v. What is the speed of the body far away from the Earth? Far away. This is very important because we are going to use this. Ignore the presence of Sun and other planets. Now escape velocity of projectile from Earth, we know that it is 11.2 given in the question also. Now this Vp, that projection velocity Vp, is given by 3v escape. This is v escape. Now mass of the projectile is m. The velocity of projectile far away from the Earth, Vf, let us assume it to be Vf. So total energy of projectile on Earth was what? Half mv square minus half mv escape square. This was the total energy. Now gravitational potential of the projectile, which is far away from the sun, far away from the Earth in this case, is 0. That is why I told you that we are going to use this far away. We know that gravitational potential at far away point is 0. So what we will do here is, we will just have the total energy far away as half mvf square. Now we compare these two, or we equate. This is the total energy on the surface, on the Earth, and that is the energy at far away point. We equate it, half m cancels out. Vf can be computed because we know that Vp is 3 V escape, and finally we get V escape into under root 8. V escape was 11.2, so you get 31.68 km per second. A satellite orbits the Earth at a height 400 km from the surface. How much energy must be expended to the rocket the satellite out of the Earth's gravitational influence? Which how much energy you have to give to the rocket so that it is out of the gravitational influence. Mass of satellite is 200 kg, mass of Earth is this much, radius is given, and gravitational constant is also given. So mass of Earth is this much, mass of satellite is 200 kg, radius of Earth is given, universal gravitational constant, and height of the satellite 400 km. Just change them into meter, everything. So total energy of the satellite at h will be what? Half mv square plus minus of gme m by re plus h. Now orbital velocity of the satellite is what? V equal to under root gm by re plus h. We know this. So v square will be what? Gme by re plus h. Why not to equate this velocity here, v square? So we have just placed this value here, and this becomes half gme m by re plus h. This negative sign indicates that the satellite is bound to the Earth. Now this is called the binding or bound energy of the satellite. What energy will be required to send or to throw out this satellite from the orbit? That will be equal to minus of this energy, so it will become plus. This much energy has to be given, and this is the energy to be expended. So we'll just take this with a plus sign, put these values which we know in the question given. It will be 5.9 into 10 to the power 9 joule. Two stars, each of one solar mass is this much, are approaching each other for a head-on collision. When they are at a distance of 10 to the power 9 km, their speeds are negligible. What is the speed with which they collide? The radius of each star is 10 to the power 4 km. Assume the star to remain undistorted until they collide. So they are like this, then they collide. This is r, this is r. Now their distance is 2r here when they collide. So the mass of each star, because one solar mass for each, radius is also given 10 to the power 4, convert it into meter. Distance between initially is 10 to the power 9, convert it into meter. Now for negligible speed, because it is given that the speed are negligible, it is given in the question. So we assume that v equal to 0. So what is the energy when they are separated by a distance of r? Half mv square plus minus g m by r, because both mass are same, we are writing the same mass, but velocity is 0, so we can put it as 0. So it will be minus g m by r. Now consider the case when they are actually colliding. So velocity is assume it to be v, and the distance between them are 2r. So the distance is 2r. Now what is the kinetic energy of both the stars? Half mv square plus half mv square, both are same, so it becomes mv square. The potential energy of both of them when they are colliding, the distance is 2r minus gm m by 2r. So total energy will be mv square plus of minus gm m by 2r, which is like this. Now let us equate this energy with this energy, because initial and final energy has to be same, law of conservation of energy. And now we get v square, because one m will be cancelled, take it on the right side, put the values which are given, you get velocity equal to 2.58 into 10 to the power 6 meter per second. Two heavy spheres, each of mass 100 kg, radius is also given. They are placed 1.0 meter apart. Now what is the gravitational force and potential at the midpoint of the line joining the center of the sphere? Is an object placed at that point in equilibrium? If so, is the equilibrium stable or unstable? The answer is that it will be in equilibrium but unstable equilibrium. First, let us find out the value. The explanation is something like this, but these are the answer. There is 1, 2, distance x, radius 0.1 meter, distance 1 meter, distance x is the point of the equilibrium. So the mass of each sphere is 100 kg, separation is 1 meter. This x is the midpoint between the sphere, gravitational force at this x is 0. So this is because the gravitational force which is exerted by each sphere, by this and this, they are in equal and opposite direction. That is why it is at equilibrium position, the value will be 0. So the gravitational potential will be what? Minus gm by r. This is r by 2, this is r by 2. So minus gm by r by 2 and plus of minus gm r by 2, which gives you minus 4 gm by r. Put these values, we know all these values, it will be this value, and this is in minus. So any object placed at this x will be in equilibrium state, but it will be unstable. Why? Because any change in the position of the object, either this or this, will affect in change in the effective force in that direction. That will be instability. A geostationary satellite orbits the Earth at a height of 36,000 km from the surface of the Earth. What is the potential energy of Earth gravity at that site of this satellite? We have to take the potential energy at infinity to be 0. Mass of Earth is given, radius is also given. What will we do here is, the distance of the satellite from Earth is what? Oh, this is 36,000, this is 6,400 kilometer. So 6,400 plus 36,000 gives you 4.24 into 10 to the power 7 meter. We have converted it into meter. Now what is the gravitational potential? V is given by minus gm by r. These values are known to us. Put this value, we get V. A star which is 2.5 times the mass of the sun and collapsed to a size of 12 km rotates with a speed of 1.2 revolution per second. These are neutron stars, extremely compact stars of this sort are known as neutron stars. There are certain stellar objects called as pulsars, which also belongs to this category. So when an object placed on its equator remains stuck to its surface due to gravity, let us see the value of g, what it comes. Then we'll say that it remains stuck or not. Mass of sun is also given. So acceleration due to gravity, we know g equal to gm by r square, where m is the mass and r is the radius of the star. But the outward centrifugal force, there is a centripetal force, there is a centrifugal force. So outward centrifugal force acting on a body, say mass at the equator of the star, will be mv square by r. We can write v equal to r omega. So it will be m v r square omega square, or you can say m r square omega square by r. So 1 r cancelled, so 1 mr omega square. This we will use. So the acceleration due to gravity with this equation will be this number. We know all these values, gm by r. Now inward force due to gravity, we know that mass into acceleration in this case is gravity only. So we'll put this value. So inward force will be m into this value. Now what will be the outward centrifugal force? mr omega square, as I said here. We find out mr omega square. We'll put this value, omega can be given by c. This is also given, revolution per second. So we just put this value, we get m into, we'll just solve them. So we get m into 1.06 into 10 to the power 6. And since here the inward force due to gravity on a body at the equator of the star is many times more than the outward centrifugal force, the body will remain stuck to the surface of the star, it will not move. A spaceship is stationed on Mars. How much energy must be expended on the spaceship to rocket it out of the solar system? Mass is given, mass of sun is given, mass of Mars is given, radius is given of Mars, radius of orbits of Mars is given, and capital G is also given. So let us assume that r be the radius of the orbit of Mars, r dash be the radius of Mars, m be the mass of sun, and m dash be the mass of Mars. Small m is the mass of spaceship, and the potential energy of spaceship due to gravitational attraction of the sun is minus g capital M small m by r. Now potential energy of the spaceship due to gravitational attraction of Mars will be minus g m dash here or r dash here. Now since the kinetic energy of spaceship is 0, so total energy will be what? Half mv square we cannot use. So minus g m by r minus g m dash m by r dash. So this is the scenario. Now what will be the energy required to you can say rocket out or throw out the spaceship from the solar system? This will be minus of this whole. So minus minus plus, so total energy of spaceship, so this much. So we'll just use this value because minus minus become plus. This much of energy has to be expended to throw it out of the you can say orbit. So these values we are known in the question, all these are known. Just put this value, you get this value. A rocket is fired vertically from the surface of Mars with this speed. If 20% of its initial energy is lost due to Martian atmospheric resistance, so 20% is lost, so 80% is remaining. So 80%, that is 2, 2, 8, 4 by 5, 4 by 5th times the energy is retained. How far will the rocket go from the surface of Mars before returning it? Mass of Mars is given, radius of Mars is given, g is also given. So here what we will do, the initial kinetic energy was half mv square. Initial potential energy was minus gm m by r. Small m is the mass of the rocket. Capital M here in this case is the mass of Mars, radius of Mars r. So initial energy will be simply half mv square plus of minus gm m by r. This we know. Now 20% of kinetic energy is lost, so 80% will be remaining. This will be 4 by 5 of half mv square minus gm m by r. This becomes 0.4 mv square minus gm m by r. Now when the rocket reaches the highest point, at h the kinetic energy will be 0. So only potential energy will be there, and we have to add a h because it has gone up to h. So we have to equate this one with this one. We equate them, we rearrange them and try to find out h, take everything on the right hand side, and this values we have known in the question. Put this value, you get 495 km. So these are the question and answer on gravitation. Thank you so much and take care of yourself.